It's my great pleasure and honor to introduce you, Yury, an old friend. First of all, I'm privileged to collaborate with you and to keep in touch with you, visit us in Israel. And I don't think I will exaggerate saying that Yury is one of the most prestigious and prolific material scientists in the world. He's a real leader, innovative, with a lot of innovative capabilities and also performance. In terms of statistics, we're talking about H factors that reaching nearly 200, just to give you the idea, and many more. I think that more something. Also, the number of citations also is something like, I believe will reach soon at 200,000 citations, etc., and many hundreds of papers, and the performance is amazing. Yury is in Drexel University near Philadelphia. He works in pioneer the development of new materials, starting with unique carbonaceous materials, and then to more complex materials. We'll hear about some of them in this talk. This year, in 2022, we opened a unique center at Bar-Ilan University, a center of energy and sustainability. We are now 55 research groups working on energy, networks, engineering, regulation, climate problems, planet studies, geography, ecology, education for reserving and restoring the environment, all aspects of environmental studies. We have also, we will start very soon, in the next academic year, in a few months, we'll start a school of sustainability, so people will be able to receive degrees in sustainability. It will be multidisciplinary. So I think that we are facing now a real challenge with the climate crisis, with the global warming, and our energy economy has to be well modified. So we won't destroy our life on Earth. And I think that this talk will deal with materials that can help us with this big energy challenge that we are facing. So Yury, again, we are honored and privileged to have you with us. We are inspired of your work. We at Bar-Ilan University are very happy with the collaboration, the ongoing collaboration, and the long-term friendship that we developed. And I believe that now I will let you to start your talk. So thank you for being with us.
Doron, thank you very much for your kind introduction. Let me share my screen with you and open the presentation so that you can see what I'm going to talk about today here. And I will discuss a large family of materials, which we call MXenes, which we discovered with colleagues and students at Drexel University a bit more than a decade ago. For people who are not familiar with the topic, last time I gave a seminar at Bar-Ilan University before COVID, so probably about 3 years past since that. Those are layered, two-dimensional, actually, carbides, nitrides, carbonitrides, and related compounds. So if you look at these structures at the top, and let me switch to the laser pointer. Those are radioatoms are metal atoms, titanium, moly, niobium. Black dots connecting them are carbons and nitrogen. And you can see also functional groups on the surface. And this is a very large family of materials that I'm going to discuss today. The common variety of flavors, colors, plasmonic properties, optical, electronic properties here. And Doron mentioned that we're facing all problems of how to develop sustainable economy, how to more efficiently use energy, and we're trying, instead of burning oil, you make materials, minimize waste. So materials have really been determining the progress of humankind over decades. If we have better materials, we can develop better technology. And two-dimensional materials, starting with graphene, have really been considered the future. And the reason is that you can assemble them like a brick by brick put together to create new materials, metamaterials, assembled materials without waste, with combination of properties that no other material can give to you here. And I will give an example by using this MXenes and tell you a little bit first about synthesis properties of these materials, and after that about their potential use in energy storage. But I will not talk about any specific kind of like a battery or supercapacitor. And of course, you have great experts, including Professor Aurbach at Bar-Ilan. I will describe general principles. What do we need to know and learn about these new materials to be successful in use of those materials and applications here? So, but first let me tell about a couple of words about myself. I was born and raised in Ukraine. I got all my degrees from Kyiv Polytechnic University in Ukraine. And actually, this is a picture I took shortly before the war when I was visiting in the fall 2021, my Kyiv Polytechnic. This is the main building of the university, with my father and my brother, who both are also scientists, both have PhD degrees. My father was professor for a long time. He still lives in Kyiv. He's almost 92 now. And my brother is now with us. He actually founder of a company, Carbon Ukraine and Material Research Center, which have been working with us for a long time and currently organizing help to Ukraine being in the US here. But I've been working for 22 years in Philadelphia. For people who don't know the location, this is between New York City and Washington, D.C. on the US East Coast here. And former Dean, Professor Gogotsi, invited me to join Drexel 22 years ago in the year 2000. And I'm still working here. I still feel happy and satisfied with what I do. And you may see that Drexel University main building somewhat resembled style-wise Kyiv Polytechnic main building. They were built at about the same time at the turn of the 19th century here. But the building where I work now is a much more modern. You can see we are not far from downtown Philadelphia. My lab occupies the entire floor in this glassy modern structure. And you can go to our website to learn more about our laboratory research activities we have here. With this, let me move to the main topic of my lecture today, MXenes. What are those materials? As I already mentioned, those are carbides, nitrides of transition metals, just like other two-dimensional materials. And I'm sure everyone is familiar with graphene, moly-disulfide, probably chalcogenides have been very popular in Israel largely also thanks to research of Reshev Tene. Those are nanometer thin materials, just a few atom in thickness, typically 1 nanometer or less. But they have a couple of very, very important characteristics which distinguish them from all other known 2D materials. Many of them are first really good metals. They have conducting metal cores where d electrons of transition metals contribute to metallic conductivity. Recall, graphene, which is very well known and often praised as a good conductor, is in fact not a metal. It's a zero band gap semiconductor. You need to create defects or dope it to have the carriers. MXenes, many MXenes are really good metals with a high density of states at the Fermi level with a high concentration of carriers. But they are very unusual metal. Their surface is typically terminated with oxygen hydroxyl group, which is shown here in this picture. Can be halogen, chalcogens here. So it looks like largely transition metal oxide or chalcogenide surface. Moreover, we can change these functional groups, modify them, and we don't kill the conductivity. Unlike in graphene, when you put OH on the surface in oxygen, make graphene oxide, and conductivity drops by 7 orders of magnitude. And we still can tune the Fermi level of these materials, like in semiconductors. So imagine, this is a metal which behaves like clay, dissolves in water because of oxide-like surface, when you can do surface redox without killing conductivity, and in which, like in a semiconductor, you can tune the Fermi level. No other material, to the best of my knowledge, offer such a possibility here. Moreover, they come in a variety of different structure. We call them like a 2-1, 3-2, 4-3 materials, just based on the number of layers of transition metals and carbon nitrogen. 2-1 will be 2 layers of transition metal and 1 carbon nitrogen, and so on. And there are a variety of them. You can see that we can make materials in all these groups. Michael Nagib, who is a currently professor at Tulane, was a PhD student at Drexel, working with myself and Professor Michel Barzoum. When the first materials was discovered, the first was titanium 3C2, and this is a paper published in 2011 with MXene on the cover of Advanced Materials, which announced discovery of this family of materials here. There is much more now. Last year, we put together a virtual issue of Advanced Materials to celebrate 10 years of progress in development of MXenes. And you can see in the past few years, number of publications, number of citations grows dramatically. About 2,500 papers were actually published on MXene just in 2021. And as you see, every year, new materials have been added to this very large family of two-dimensional materials. So how do we make them, and where does the name come from? There is a large family of layered ceramic materials known as MAX phases. For example, titanium 3, aluminum C2, titanium 2, S, C, and others here. Professor Michel Barzoum, my colleague at Drexel, was one of the pioneers in the field. He did not discover the family. They were discovered by Novotny in the 60s, but he really developed them into materials here. So what we did, we took this MAX phase, like titanium 3, aluminum C2, and we removed by selective etching the layer of aluminum. We have been using the method of selective etching for making carbon materials, removing all metals from carbides, for example, for many years. But here we just remove one metal, A element. So if you take A element from MAX phase away, what you're left with M and X, and this is where the name MXene came from here. What is important here? Those are layered ceramics. You can see a picture of the structure here, but unlike ceramic disulfide or graphite, you cannot just easily share them and make two-dimensional structures because there are strong chemical bonds between M element and A element. And that's why you have to etch them to remove these layers. However, after you remove layers of atoms connecting carbide or nitride sheets, you end up with loosely bonded by van der Waals or hydrogen bonds layers of carbides and nitride. You can see, for example, here 3 layers of transition metal. You cannot clearly see between them carbon atoms here, but you can see now there are gaps, non-uniform, larger, because now there are weak bonds between them. And then when you have weakly bonded layered structure, looking like exfoliated, thermally expanded graphite or vermiculite clay, say you can exfoliate them, delaminate into single layers, monolayers, making flakes of materials here. What is important? If you look at possibilities in the field, M elements are all these elements in blue, and you can add rare earth metals here. A elements we remove are red here. Aluminum, silicon, gallium are the ones that so far have been etched away successfully from those materials here. You get carbon and nitrogen. Multiply just the number of transition metal, like a 12 by 2, and 4 different structures available, and you already get about 100 of compositions. But we can have on the surface all those elements, OH, amino groups as well, at least 10 surface termination. Multiply by 10, you end up with at least 1,000 of stoichiometric compositions possible for MXenes. About 50 have been made so far, but what is important, we can also make solid solution. We can mix and match carbon and nitrogen, making carbonitrides or transition metals, which makes really an infinite number of materials possible. Moreover, we can make not only like a simple structure that I showed you from the beginning, it's possible to make atomic sandwiches, like out of plane ordered MXenes, where the outer layer is, for example, titanium, moly, or inner layer is titanium, or outer layer is chromium. And it's possible to make also in-plane ordered structures when there are alternating atomic columns of different elements. And if you remove one of them, for example, like a yttrium and tungsten, or moly scandium, if you remove one of them, which is more active, like yttrium scandium, you end up with a material structure when you have like a monatomic vacancy lines on the surface things here. So basically, we push atomistic engineering to the limit. And it's possible to make high-entropy multi-element materials where 4 or 5 transition elements are in the same structure created here. So basically, sky is the limit. What do we have right now? We have probably the largest known possible family of two-dimensional materials. Definitely the largest family of inorganic materials discovered over past few decades, which can again be used as building blocks for future materials devices, and also combine with other 2D materials, with graphene, metal chalcogenides, oxides, to achieve combination of properties that no other system can provide. So what is also important? We have a very large family of materials. We have ability to design at the atomic level, create structures which are needed to us, modify surface chemistry. But you have probably heard about discovery of new two-dimensional materials many, many times here. Majority of them remain scientific curiosity. Monolayer gallium nitride hidden under a layer of graphene because it will immediately oxidize otherwise. Other materials, which may be interested scientifically, but will not make a difference in technology. But MXenes were produced by wet chemical etching. You can see here, for example, one of our reactors designed by Materials Research Center, Ukraine, which was founded by my brother, Alexey Gogotsi. And you will see a PhD student in my group who is holding 1 kilogram of MXene produced in our lab here. Why it's important? When you have a large amount of materials made, you can really talk about energy environment applications, which requires more than milligram of materials. And moreover, when you produce these materials, which is what you see here, we call it MXene clay. It's like a wet, slightly wet powder after synthesis. We can disperse it in water. Again, pure water. No surfactant is needed, unlike in the case of graphene. Similar to, say, graphene oxide. You put it in water and it gets dissolved because the zeta potential of majority of MXenes at close to neutral pH is between -30 and -80 millivolt. This is an example of titanium 332, the most common, the first discovered MXene, which I will be largely using to illustrate my talk today. Actually, TX, I forgot to mention, stands for surface termination. After synthesis in acidic electrolyte, usually we use HF, we get oxygen, OH, fluorine as a surface termination on this material. Things here. I will not go much into details here, but what is important? We start with ceramic powder. It's just a layered ceramic produced by conventional ceramic technology, can be produced by self-propagating high temperature synthesis to minimize use of energy and decrease the cost. After that, we etch it using, for example, lithium fluoride HCl mix or dilute HF, or there are lots of other recipes which I'm not going to discuss today, from emulsion salts to hydroxide bases to electrochemical etching here. And after etching, we dissolve it into solution here. You can see an example of, for example, very dilute solution. We just put a droplet of solution in water. Like about maybe 10 milligram per milliliter solution we use, for example, for inkjet printing, for coating fabrics, fibers, and a viscous slurry, which actually has liquid crystalline property, usually at certain concentration, which can be used, for example, for drawing fibers or for doctor blading, making electrodes or current collectors for batteries here. So what is important basically here? Again, we can prepare aqueous solution. Again, it means pure water, no toxic additives, no binders, no surfactant needed. And from this solution, we can manufacture whatever we want, because we can basically move from dilute liquid to solid-like behavior even at high concentration. And if you have a colloidal solution of particles, in this case, two-dimensional, typically monolayer or few layer flakes with the size of from hundreds of nanometers to 10, 20 micrometers, you can basically use any known technique to manufacture. It's possible to use printing like inkjet printing or screen printing. You can fill a pen, fountain pen, or any other pen and draw with MXenes. You can use 3D printing to create structures. You can make coating by spin coating, spray coating, dip coating, any technique you name, whatever you like. And it's possible, of course, to create 3D structures, including aerogel by freeze drying and so on. So now, we have a very large family of materials, huge, with 50 reported MXene roughly. It's just clearly the beginning. We can manufacture them in large quantities. We can process them very easily from colloidal solution without any toxic solvents or special tricks. But it's only good if these materials bring something new to the table, if they bring some useful properties. Let us look at what they bring. One of the most important properties from MXenes that largely distinguish them from other 2D materials here is their very high metallic electrical conductivity. Actually, values over 20,000 Siemens per centimeter already have been reported, but I would say 20,000 is a reliable value for multi-layer film like that, where there are thousands of junctions between flakes. So again, it is like a vacuum filter to spray coated film. You just put it on the surface, dry it, and you get a metal. But they have all this oxide, hydroxide-like or chalcogen coated surface, which gives them opportunity, for example, for reversible redox. But there is also something. They are strong and stiff. They have strength single layer flakes as measured experimentally and predicted theoretically in the range of 20-30 GPa, which is stronger than any solution process to the materials here. And it has direct and indirect implications here. For example, we can make really strong films, which can be used for also structural application or current collectors, like metal foils, but also because of this, we can produce in solution large flakes. For example, these flakes are all single layer flakes of titanium-32, have size of about 20 micrometers. I've never seen oxide or chalcogenide flakes of that size produced from solution. They will just simply break because they're not mechanically strong enough. This strength allows us to make larger size flake. There are other things. You have seen variety of colors, which are plasmonic colors, which allow us to make electrochemical plasmonic devices. We can tune surface chemistry in these materials. But the key thing is here. Those are single layer crystalline flakes, as you can see from selected area diffraction. And we can tune those materials. We can select from variety of structures and surface terminations, and we can actually finally change them by mixing solid solution or modifying surface terminations. So we have materials which properties can be modified, finely tuned for specific application. There are many other interesting properties have been predicted. Topological insulators in this system, ferromagnetic, antiferromagnetic two-dimensional materials. Some of them, like a superconductivity, was confirmed about 2 years ago by Dmitry Talapin first. But some other properties are still to be demonstrated, like ferromagnetism in single-layer MXene flakes here. A lot of interesting things here. And many of them are already finding application. For example, tunable work function is used in solar cells, optoelectronic application. And you see, by changing just surface termination in this material, from OH to oxygen, one can go from about 2 to about 6 electron volt. By changing, adding extra layer of titanium, for example, inside the structure, so like a 4 layers, 2 molar outside, 2 titanium inside, you can see you change density of state in the material. And of course, each of those materials will have a distinct set of optoelectronic properties, which again can be controlled by the number of layers in the structure, type of metal, carbon, nitrogen, or their mix, and surface terminations. Moreover, when we look at these materials and an assembled film I showed you before, we have additional options. We can graft molecules on the surface, again, without killing conductivity. We can also intercalate molecules and ions. And alkaline, for example, cations in general, can be intercalated spontaneously because of negative surface charge on MXene surfaces here. So we have another option for tuning properties of this material here. And MXenes, at least titanium-32, many others, have long-term stability even in solution and years in open air and films, which again allows practical applications here. So what does it mean? we can manufacture by using these materials, for example, like electrode film. And you can see it's actually stronger than aluminum foil that you use to wrap your breakfast. It has strength of 570 MPa, 1 micron film, just after Dr. Blade coating and drying. And it has high conductivity. And you see this is like a meter-long film produced here. So again, if we can produce large amount of material, we can use it not only for electronic optic sensors, but we can go towards catalytic environmental energy storage application. And maybe one day, like graphene, we will be able to use them even in construction, because if you look at, for example, composition of those materials, the most common one, titanium 3C2, titanium 2C MXene, titanium 3CN, they contain very common earth-abundant elements. And as a result, it means that they can potentially be produced in large quantities at moderate price. Now, let me wrap up this first part of my talk. We have now this very large family of materials that can be manufactured into a variety of structures, variety of compositions, where we can finely tune structure, composition, and it means properties that can be manufactured from dispersions in water, colloidal dispersions in water with no additives, and which bring a variety of unique properties. Naturally, combination of high conductivity, oxide-like, say, surfaces, transition metal on the surface, led to an ability to intercalate ion, led to variety of electrochemical applications, materials, in particular in all kinds of supercapacitors, batteries, but also many others, including from hydrogen storage to solar cells, to electrocatalysis and variety of electrode and electrochemical devices. I gave just a few references to initial papers here. I'm not going to discuss them all here. What I would rather do, I would rather talk about what we are trying to achieve, developing energy storage solution, and how and why MXenes can help us to achieve this goal, and what are also challenges and obstacles to overcome to really make these new materials work for us. So let's look at this Aragoni plot. I'm sure most of you are familiar. It comes from our review with Patrice Simon, my long-term collaborator, which shows differences in energy and power densities for electrochemical capacitors, double layer capacitors marked here, which store energy electrostatically by just attracting ions to the surface of material, which give us very high power. This is a charge-discharge time you see going to milliseconds, but low energy values. And of course, you all use batteries, lithium-ion batteries, for example, marked here by a green stripe, which give us much more energy, like 2 orders of magnitude more than double layer capacitors, roughly. But they require longer charging discharging here. And this areas marked in dashed line show the regimes where they can be run, but with quick degradation and damage and short lifetimes. So what does everyone want? To get somewhere in this area, to get into, say, minutes charging time for energy storage devices. Like Elon Musk promised, we will have car batteries charging within 5 to 10 minutes. At the same time, storing as much energy as current batteries. And this is called high power, high energy storage solutions. And it seems to be that it's really easy to reach, a little bit push up. But note, this is a double logarithmic scale. To get there, from there, we really need to increase by about like a 2 orders of magnitude the power of batteries. And lithium-ion batteries have already been pushed very close to their limit. Or we need to increase again by maybe like a 2-3 orders of magnitude energy density of capacitors here. So what do we need to get here? Why can't we get it from common batteries or supercapacitors here? Supercapacitors store energy just in a double layer, electrostatically. They simply fundamentally cannot in this way give us more energy. So to get more energy, we need to have charge transfer, electron transfer. So we need a redox energy storage process. Why can't we just take conventional battery materials and push them to this rate easily? There are 2 reasons for this. One, whenever you have a bulk material, even small particle, solid state diffusion will always be a limiting factor. But second, what does it mean, for example, to quickly charge a battery within a minute? It simply means running a high current through your device. And if your device uses poorly conducting materials like oxides, it transforms into a heater. Basically, draw heating will lead to enormous losses of energy and also will result often in simply quick degradation or even failure and fire. So what do we need? We need materials where there is no bulk diffusion, where all the processes happen on the surface like in a supercapacitor. Two-dimensional materials provide exactly that. Their entire material is the surface pretty much. We need a material which will be able to do redox energy storage. So transition metal on the surface of MXene is exactly this type of materials: vanadium, niobium, titanium, moly, all commonly used materials in redox energy storage. I just mentioned to you that we need materials which have high conductivity. Titanium 332, if you consider, for example, what I mentioned to you, like a 20,000 Siemens per centimeter, has about 2 orders of magnitude higher conductivity compared to activated carbon used for make these high rate capacitors here. And we need ionic transport, which is again can be done in galleries between the layers of materials. So potentially, materials like MXene may provide ideal solution for energy storage. We can pack 2D materials densely enough that we will have high volumetric energy density. We can achieve very high metallic conductivity, which will allow very fast charging. We can have redox reactions, and we can transport variety of ions between the layers, even like a multivalent ions like aluminum, magnesium, and other things. So this is a promise. Now, it appears to be not as easy as expected, of course, because whenever we deal with new materials, we need to learn about them. We cannot just take MXene, put into conventional supercapacitor and battery configuration and tell everything is great. We will get much better performance now. Let us talk about how they behave and what happens. And let us start with very simple aqueous systems, solutions of lithium, sodium, potassium salts like sulfates, which provide double layer storage, and see what happens when ions go in. One thing you may wish to notice that some ions will lead to shrinkage. For example, magnesium, because of electrostatic contraction and positively charged ions get between the layers. But some others, for example, potassium, will virtually lead to no change in despacing of the material. So basically, electrode will not swell when these ions go in. This is very important information because unless we want to develop an electrochemical actuator, we want to have minimal change in dimension of the electrodes. Also, some ions will come with water molecules, cosmotropic ions, which will bring water in, like lithium, magnesium, aluminum. Some others will push water out, like cesium or tetraethylammonium. And some other ions will lead to minimal changes in the number of water solvent, basically, when intercalated in the film. By the way, this work was done in collaboration with Professor Doron Aurbach. So, Doron, sorry for a typo in your name here. Michael Levy and Nathaniel Spiegel. And we have done a lot of work together studying ions between MXene layers and others. I'm not going to talk about it today intentionally, simply because I trust you are familiar with this beautiful work, but EQCM has been, and EQCMD have been very important tools in understanding behavior of ions in those systems here. So we take binder-free electrode, we can get ions, and we need to understand what happens, how ions get. Moreover, even if you know that ions get in and get in with such a number of molecules, ions between MXene layers will behave differently. For example, cesium, magnesium will stay solvated in between MXene layers, somewhere in the middle. What you can guess from this, there will be very little polarization or charge transfer. They bring some charge with them, so they can provide electrostatic, more or less capacitive energy storage. But lithium, sodium, for example, will come very close to the surface and actually interact even with MXene surface. So it means that they, even from neutral solution, can provide much stronger polarization. And as a result, what you will see as a result of interaction of actually electron shells, in this case, hybridization of orbitals with the surface, lithium, sodium will give significantly higher capacitance compared to, say, cesium and magnesium, which stay in the middle. So that's, again, very important to understand, to select ions that can provide us more charge. And in spite of the fact that, say, magnesium is divalent, and one would guess, okay, we bring larger charge between the layers here, but in fact, you get less energy storage from it here. Moreover, MXenes, just like a graphene oxide, are hydrophilic unless you modify the surface. I'm not going to talk about it today. And they can also swell in wet environment or when placed in environment with electrolyte. Actually, this transition can happen sharp. You can see two diffraction peaks. They basically go from a monolayer to double layer of water, just as we increase humidity here. So again, this is something that is important for storage and application, how to minimize hydrophilicity, and we need to be aware of it here. Finally, it's not only ion behavior differs when we have confinement between MXene layers. The solvent behavior differs as well. You can see here results of modeling by using molecular dynamics, actually reactive potential reacts effect, and experimental data for neutron scattering to study diffusion coefficients of water molecules between layers of MXene without and with ions intercalated. And what you will find that diffusion coefficient of the solvent of water actually changes by a factor of 2 or 3, by 2 or 3 orders of magnitude when ions are intercalated. So water becomes much less mobile when it interacts with ions and solvate ions trapped in this two-dimensional confinement. So we really need to understand ions, and we need to understand solvent behavior in confinement if we are to design energy storage systems or other systems with two-dimensional materials with strongly interacting with solution surfaces. Now, Let us check another hypothesis I mentioned to you. Can we do redox energy storage in the system with high rate of promise? And in fact, yes. What you can see here, it's in protocol electrolytes with sulfuric acid. Cyclic voltammograms showing titanium 3 MXene in sulfuric acid. You can see that there is virtually like a double layer storage, like capacitive envelope at potentials close to OCV. But there is this very broad but electrochemically reversible separation is about like a 20 millivolt only between reduction oxidation peaks. And these peaks actually persist redox up to rate of 100 volts per second, 10 millisecond charge discharge, like in the best double layer capacitor. So we can have redox storage at enormous rate. We are not limited by rate of redox reaction. But as we increase the thickness of the layer, you can see this enormously high, like a 1500 farad per centimeter value, goes significantly down. And rate performance decreases because we are now limited by diffusion between the layers, very long path for an ion through the film as we go from like about 100 nanometer films to say 5 micrometer films. So we need also to design architecture of the electrode. And by the way, from X-ray, XAS, X-ray absorption spectroscopy, we know this is a reversible reduction oxidation, change in oxidation state of titanium that is responsible for this energy storage. And now I showed you result for titanium 3 but simulations done by Dean Jan from UC Riverside showed that actually many other materials may have much higher ability to store charges in same protocol electrolyte than titanium 3. And there are other surprises brought by this system. For example, when we move from dilute solutions or protocol electrolyte as showed to today, this is a CV here, to water and salt electrolyte, which are being researched by many as environmentally friendly, safe electrolyte, which allow us to achieve wide voltage window in a aqueous system. We observed this couple of peaks, which look probably to most of you as a typical redox couple, reduction oxidation under positive potentials. First idea is there are anions which are being reversibly oxidized, reduced here. However, it appeared not to be really the case. And actually the first indication was provided by EQCM study done by Nathaniel, which again, I'm not showing here, assuming you may be familiar with this work here. And I truly did not believe there is no like an ion inside. But after that, X-ray diffraction, atomic force microscopy study showed that we see have drastic change in the spacing. We simply close completely, we push all cations intercalated between the layers lithium out of the system when we observe this peak. And after that, they rush in, leading to expansion of the electrode upon specific potential, when potential goes down. So we really have intercalation, deintercalation of partially salvated lithium ions. So we have this unusual effect of drastic change in dimensions. And similarly, interesting, unusual things we observe when we go to non-aqueous electrolyte. For example, lithium TFSI in different solvents. And people who work on supercapacitor especially know that acetonitrile is considered to be like the best solvent given the highest conductivity to electrolyte. But when we use acetonitrile, we got actually the poorest performance, lowest charge storage, lowest capacitance of this material. Surprisingly, in PC, we got much more charge storage, like a double values. And even DMSO, which was used actually in earlier stages in batteries and a solvent, we observed larger storage. So how to explain it? Again, we need to go and look into molecular level, atomistic level changes. What happened in DMSO? You see there are in X-ray diffraction analysis, we can see dimensional changes of material. We see large interlayer spacing. With 1 nanometer thick layers, we have something like a 9 angstroms of interlayer spacing here. With a set nitrile, the spacing decreases, roughly like a 3-4 angstroms will be between the layers, but there are still small variation in spacing. But when we take PC, we observe no dimensional changes. And actually the spacing shrinks to 11 angstrom. It means that something like a little bit more than an angstrom of space between layers of MXene. What does it mean? Simply, in case of acetonitrile, we get ions, lithium is green here, going to the surface, transferring charges. But there is a layer of molecules of solvents separating the sheets, like insulating them, leading to poor performance. In case of DMSO, we get actually very good rate performance, but there are a lot of ions with solvent molecule. DMSO goes together with lithium in, and we get lithium ion at the surface, and we get lithium ions between the layers. So we have large dimensional variations. Maybe good for some applications, maybe good for, again, electrochemical actuators, robotics, but not good for batteries. In case of PC, we get only lithium between the layers. So we get more energy stored, and we have no fluctuation of interlayer spacing. I hope this gives you an idea of what we can do. And this very recent Nature Energy paper, which actually already online appeared about a month ago, published with a group of colleagues, shows that we can basically in these 2D systems go all the way from double layer type capacitances showed to you to battery-like behavior. We get complete desalvation of ions, and it all determined by degree of desalvation and confinement of ions between layers of two-dimensional materials. And as we know and understand these processes, we should be able to design useful devices here. Again, as I mentioned, I'm not going to tell you how to make a lithium-ion battery or sodium-ion capacitor or use it in a lithium-sulfur battery, the MXenes here. I hope the information I showed to you will help you to get some guidance and idea what needs to be done to understand behavior. What I wanted to mention at the end here, that when we have 2D materials, we can also do things we cannot do with conventional materials. We can make flexible devices, printable devices. We can make devices in a chip that are about 100 interdigitated supercapacitors here, which actually show extremely high rate performance. They can operate at 130 hertz, can do AC-DC conversion like electrolytic capacitors here. We can actually make even like a textile devices. We can incorporate MXene into fabric fibers and knit energy storage devices here. We can also use MXene as passive element. You remember I showed you 1 micron thin foil with the strength of aluminum foil produced simply by Dr. blading and drying MXenes here. So we can make current collectors for cathodes and anodes for a large variety of batteries. We can use it as a binder, for example, for oxide cathode materials, or even for activated carbons here, or silicon to make silicon anodes here. So there are many applications where you can use properties of materials. Again, if you understand the properties, you can understand how you can use it efficiently. Also, MXene suppress dendrite growth, and it has been shown by a variety of research groups leading to growth of lithium, potassium, other metals, zinc, parallel to the surface of materials. So basically, I think it's time for me to wrap up. We started a bit later, but it comes to an hour. There are many applications emerging for this large family of two-dimensional materials here. Energy storage and harvesting, like a triboelectric nanogenerators and others, is very large part of this. But there are many other applications of interest: water desalination, filtration, capacitive ionization, and many others, of course, also in electronic communication, sensing, medicine, and so on. Here, there is already a MXene association bringing together a company, researchers, industry, university interested in MXenes. You can go to this website or just look up MXene Association, Google it out, and join to get newsletters about latest research patents and development in the field. Finally, I would like to thank many people who contributed to this research. This is my research group. We have researchers from at least a dozen of different countries working on MXene. This is a gathering about a year ago. We have a summer party, definitely going to have one this year again, and many collaborators. I already mentioned Professor Doron Aurbach, Michael Levy, Nathaniel Spiegel, other colleagues from Bar-Ilan, but there are many other researchers all over the world, also in other universities in Israel, and of course elsewhere. And this is just a small group of people I listed here, because dealing with so many materials, we need experts in different fields. We need lots of people, and there is still so much room left for discovery of new materials, studying their properties, confirming theoretically made prediction, and of course developing energy harvesting storage solution, whether you work on water deionization or solar batteries or other ways of harvesting energy, or any type of energy storage devices, electrochemical energy, or electrocatalysis I didn't talk about today. MXenes can offer solutions here. So again, consider them here. Finally, before I finish, I wanted to mention that we will have a MXene conference at Drexel University in the first week of August. We also will have a one-day tutorial course prior to the conference on Sunday. And you're welcome to submit abstracts. We plan to have an on-site conference. Come to visit Drexel, learn about MXene, and present your results here. So please mark your calendar, join us. Also, to support Ukrainian scientists, we offer free registration to scientists from Ukraine here. And this is my very last slide. I'm going to stop here. Thank you very much for your attention, and I will be glad to answer questions.
Thank you very much, Yury. I would love to have some discussion, but just to inform you a few things about the audience. So first of all, well, I can tell you that we are doing a lot of follow-up studies on MXenes, and we verified many of the statements that you made. So it's very nice to see how the things are spreading, and indeed find application. I just want to let you know that we opened this is a joint seminar also with INREP, Israel National Research Center for Electrochemical Propulsion. I'm happy to see that there are several members. I'd like to let you know that in Israel, we have 28 research groups working on energy storage and conversion that we turned competition to collaboration. So we work in a framework where we collaborate on several energy matters. And I see we have many faces here from INREP as well. So it's a joint seminar with the Israel National Research Center for Electrochemical Propulsion. We have a representative for, I believe, in INREP with group of 7 universities in Israel. So, and I see many faces. So we have here a very broad audience. Now, Shmuel Yerushalmi wanted to ask a question. I see also a hand raising from Ava. So Shmuel, please.
Yeah, I hear.
Please.
Okay, I want to ask you next question. Is it MXene can to use for storage different types of renewable energies like solar energy, wind energy, and another forms of renewable energy?
Definitely yes. Well, again, you know, like first, it can be used. It is used. Which actually just 2 days ago published a paper with colleagues from China on use in solar cells. It's layers that basically where you can tune work function finely here. But naturally, just like battery supercapacitors that can be combined and largely used for storing energy from renewable sources. And this is where I hope most of electricity will be coming from. So short answer is yes.
I see also a hand rising from Ava.
Mm-hmm.
So you can, if you want to ask a question, so please, Ava, do you want to ask a question? Also, there is a question came in the charts. Is titanium-based MXenes are stable against oxidation in water dispersion, or is there any specific pH for the dispersion for storage? There's a question.
Okay. This is an important question, and let me actually probably pull the slide that I had on this. I did not go into detail on this here, but let me use this slide to explain. What this slide shows that titanium 3C2 MXene flakes, you can see a flake here, can stay, and this was in solution for stored.
Can you please share the screen?
Oh, sorry, I lost sharing. My apologies. I didn't realize it. Let me reshare the screen. What is happening? Sorry about that. Okay, we are back to sharing.
Good.
Yes. Yeah. Okay. So this is a slide I meant to show. So you can see flake of titanium 3C2 MXene here. This is like a say 5 micron, 10 micron flake. And you will see that even after 10 months, it still has this type of very nice regular edges. And there are only a couple of pinholes we see in some of the flakes as a result of very minor degradation. And this was stored at room temperature in very dilute solution, like 1 milligram per milliliter probably, but in a closed vial. And you see there are no changes in Raman spectra after like 6 months of storage. So first, titanium 3C2, many other MXene, niobium 4C3, tantalum 4C3, are very stable over a long time. But what is important? There must be stoichiometric. If you have lots of missing, say, carbon atoms, defects, when you etch, titanium becomes atom like in the structure unsupported. Consider to be like a, you know, like a, if there is no carbon here, this titanium atom is not supported. So it can be easily taken away, removed, and then degradation starts because you have a lot of defects. So you need stoichiometry. You also larger flakes, fewer point defects, better is stability. So it means that it depends on how you prepare your materials and also even max phase precursor. Second, there are some MXene which are very stable, as I mentioned, niobium 4C3, titanium 3C2, niobium 2C. But there are some MXenes which are not very stable. V2C used to be known as the least stable MXene because it would oxidize after synthesis in solution unless you make it into a film within virtually hours. So my student would normally transform it into whatever they wanted to do with same day after synthesis. But just like 2 months ago, we published a paper showing by optimizing surface chemistry and synthesis process, we can increase lifetime in solution to about 4 months, and after that can redisperse and make films that works just fine. So what does it mean, basically, the message? MXenes can be very stable even in solution and store for a long time, but it requires you to make materials which are not defective, which don't have surface terminations that can hydrolyze, leading to hydrolysis also of the entire material. So it requires some effort, and some of them are more stable than others, but all of them can be processed from aqueous solutions, and all of them have sufficient lifetime that will allow you to make devices. And also, we ran in aqueous solution titanium 332 devices, for example, for close to 1 million of cycles without noticeable degradation. Hope this answers your question.
Okay, thank you so much, sir.
You're welcome.
Are there any questions or comments? In fact, I don't see further comments. So I think that I think that we can conclude. And thank you again, Yury, from this very comprehensive talk. It was exactly what we looked for. We had a broad audience here, so it was very important to give an introductory, but yet, so you combine very nicely the general description, also some specific important data and progress that you are making. So I think that this talk really reached its goal in the best way. So
again, Doron, thank you very much again. I was glad to see a crowd approaching 100 people in a peak time. And again, my goal was to introduce you to this very large, exciting family of materials, which is still growing, so that you may consider exploring those materials for whatever applications you have for them. Again, thank you very much for your attention. And if you go to our website, nano.materials.drexel.edu, you will find lots of information. You can download our papers, learn about what we do with MXenes. And of course, if you have further questions, and actually I see one about the stacking behavior of MXene sheet here, just write to me. I will be glad to answer them directly.
Yury, it's very easy to follow you, in fact. It's very easy to follow, easy and inspiring. So we'll keep in touch, and thank you for this opportunity. And as you said at the beginning, hopefully we'll see each other very shortly, face to face.
I hope very much so.
In 3D and then in 2D.
Yeah, thanks.
I thank all the audience for being with us. Nice audience, really. So I'm very happy about this event. Thank you very much.
Have a great day, everyone. Goodbye.